We're going to talk about probes today, and really the intent is to kind of educate you about probes. They're a high failure item in ultrasound. And I'm going to tell you some or give you some thoughts on how you can maintain your probe fleet, if you will, more affordable. And that's really what we're looking for, right? We want quick turnaround times. We want it to be affordable if it can be. And we, clinically, we want them to be working, so we get good image quality, good patient satisfaction, the clinical diagnosis that's accurate. So we're going to cover a lot of information. It's the slides. There's only a couple hundred slides, so this should go pretty quick. That's a joke, okay? So there's only like 20 slides, but there's a lot of information. I'm going to ask some questions. I have a couple slides built in, and I'm going to ask you some questions. I really do want some feedback here, so don't be bashful. There's only a handful of us. We're all in the same industry, so let's have some conversation here, and we'll get to know each other a little bit. All right. The essential ultrasound probe, a clinician's lens. What do the clinicians see? Probes, transducers, scan heads, different names for the same things. Okay. Philips, one of the famous things about Philips is they call their probes scan heads. And if you go into a clinic and somebody calls it a scan head, they go, well, what are you talking about? So I like to give you different naming conventions for the same thing. Eyes and ears of the ultrasound system, that's a great way of looking at it. Provide detailed images of anatomy using grayscale. That's another thing the sonographers like to say is, I have noise in my grayscale. And you're like, what? Most ultrasound images are made black and white, basically, right? They're different shades of gray. So don't let that bother you. When they're talking grayscale, they're just talking the 2D image that they normally look at, okay? So a lot of them will call that grayscale imaging as opposed to 2D or basic imaging mode. All probes operate using the same fundamental principles, but have different shapes, sizes, and frequencies. Well, that's good information. And we're going to go over what the different shapes and sizes and frequencies do for us, how they benefit, how they harm us as far as from a image perspective. So we're going to go over that pretty significantly today. Easy analogy, probes are like the lens of a camera. Objects may be near or far or require a wide angle. So you just don't know what you're going to do as a photographer, right? But we have to use the correct probe for what we're looking at. And that's really what we're trying to figure out. Medical imaging professionals choose correct probe to optimally visualize structures in the body. And we're going to spend some time talking about what the correct probe is, okay? So one of the things that we have to understand is what probes, how probes work. We call it the piezoelectric effect. Basically, quartz crystals they discovered back in the old days, back in Madame Curie and all that, discovered that quartz had this unique characteristic about it. If you hooked up high voltage to the quartz, it would vibrate, sending out sound waves into the atmosphere. And the other unusual portion of it is if you hit it with a pressure wave, the same material would generate tiny electrical pulses. So it had two kind of unique properties about it. If you hooked electricity up to it, it would sing, if you will, and put out sound waves. And if you hit it with a pressure wave, it would create tiny electrical pulses. That's the piezoelectric effect. We don't use quartz anymore, but we use a glass-like substance called PZT, which is lead zirconate titanate. It's man-made now, so we don't have to go out and look quartz, find quartz that's naturally occurring. We can grow it and make better crystals. We have the direct effect, which is really the receive function. The receive function in ultrasound is where the sound wave strikes the probe, causing it to generate tiny electrical pulses. So that's what we call the direct effect, okay? The indirect effect is where we hook up high voltage to the crystals and cause them to send a sound wave into the human body, okay? So just some physics. We don't get into the math. we have the anatomy of an ultrasound probe. I don't get into a lot of the anatomy, and the reason I don't is we don't repair them in the field, right? It doesn't help us, in my mind, to go in there and say, well, I know how this probe is layered, all the different materials in it. What I want to talk to you about is what things you can see while you're in the field working on an ultrasound or walking into a room, pick up a probe and say, ooh, this isn't good, okay? And that's really, you can look at the acoustic impedance matching layer, and that's the actual acoustic lens. It has to be there. People will always, all the time, they'll look at a probe and they'll have chunks of the lens material missing. Does it still image? Absolutely. So the sonographer continues to use it. But what they don't really understand is that lens actually is acoustically matched to allow the ultrasound wave, the sound wave, to go into the human body in the correct way. So when you remove that layer, that lens, through damage or wear, it actually affects your image quality. So as soon as you see probes that have the lens material missing or damaged, then they really should be repaired. And almost, I'd say 90% of probes that have missing lens or damaged lens can be repaired. There are exceptions where they get dropped, crack the crystals. Okay, that's beyond just a lens repair. But lens repair by itself is a fairly affordable repair compared to the price of the probe. You're talking a few hundred as opposed to thousands to replace the probe. So again, for your facilities, go in there, get them repaired as opposed to replaced. You also don't have to do a capital purchase. A lot of hospitals that I've worked in, if you have to buy a new probe, that's a capital purchase and they have to get it approved at a higher level. Whereas if you're just doing a probe repair for a few $100s, you can authorize that yourself. So a lot of reasons probe repair may be a better way to go. And what's the warranty? Well, we give the same warranty as if you got a new probe. So the warranty is not an issue either. So something to think about. Backing material, again, I don't really worry about this stuff. The array, we can tell you that your array is broken if you send it in for evaluation, right? We can evaluate the array. It's pretty obvious. So if you see that the array has a dent in it, it probably got dropped or slammed against something, and it's glass. I mean, think of the material as being glass. It doesn't take a lot to crush it, okay? Housing or casing, it should be not cracked, not damaged, not separated. So if you see any of that, you should get it in, get it repaired. The longer you wait, as soon as you see it, if it's just happened in the last, say 2 weeks, there's probably no internal damage to the probe, so we can quickly repair it, and it's cost effective. If you notice it and say, it's no big deal, and you wait 6 months to a year to get it repaired, now you've had intrusion into the electronics, into the array. Now it's not going to be repairable. Now it's going to be, the cost is going to go way up. So again, the sooner you can see damage to a probe, even if it's very minor, get it out of service, get it evaluated, and we can take care of it. It's cheaper that way. Okay. Cable and strain relief. Your cables need to be intact, no cuts, no cracks. Strain relief protects it from damaging the cables inside. So if they're coming loose or broke off, you need to get those types of things. Those are repairable things. As soon as it happens, take it out of service and get it repaired. Most companies offer a loaner probe. So if we have a loaner, for example, we'll send you a loaner to put in service while yours is being evaluated. Okay. Gel is used as a coupler. It's required to get a good image if you're imaging human body, human tissue. So don't try to do without gel. It's kind of a mandatory thing, but keep in mind it does seep into cracks. So if you have cracks, it can cause problems. And frequency, I see frequency spelled wrong now. Just keep in mind frequency has an effect on your image quality. Low frequency is low resolution. Your image is going to look worse, okay? But it's going to be able to penetrate more. So if you have a technically difficult patient, which is a large patient, and you're trying to image them, you're almost stuck having to use a low frequency probe, and that's going to cause problems with your image quality. So keep those in mind. It's a trade-off in ultrasound. We're always trying to use a higher frequency, but it comes with a trade-off. A higher frequency may not penetrate deep enough to see what you're looking for. So it's a trade-off. Frequency does affect your resolution. Just please keep that in mind. All right, types of probes: linear, curvilinear, phased array. You have specialized probes, which are invasive, the TEE probes. You have non-imaging probes, 3D, 4D probes. So I just wanted to list them and kind of show examples of them. It's kind of hard. I don't like this slide too much because it's the white background. It's hard to see the probes, in my opinion. I tried to darken it up, and I just couldn't find what I was looking for. I'm sorry. So anyway, we're going to go through them and talk about each one of them. So let's start with the linear probes. Anybody know what linear probes are used for primarily? Anybody? Okay, I'll mention some things, and then we're going to ask another question. How about carotid artery? How about thyroid? How about breast imaging? Musculoskeletal? Trying to think, small parts. Those are image modes that linear is used for. What do all those things kind of have in common? When you're talking vascular, thyroid, breast imaging. Shallow, nice. They're very shallow. They're surface oriented basically, right? So what kind of frequency do you think you'd use on a linear probe? I'm sorry? High frequency, because you don't have to penetrate now. So in order to get the best resolution, you want the higher frequencies. And most linear probes range around 7 to 15 megahertz, the majority of them. Okay, so that will work really great. The shape of the beam is a rectangle. Okay, that's what your image will look like on the monitor. Okay, the width at the top of that rectangle is the width of the probe. It doesn't matter on your monitor if it's this wide or if it's this wide. It's still the width of the probe. Keep that in mind. It's not showing more than the width of the probe, even though it's much wider than what the probe is in reality. It's just showing you a bigger perspective, if you will, okay? And here we go. So here's your applications down here. Okay, normally higher frequency. Curvilinear or curved probes, abdominal OB/GYN probes primarily. Abdominal is a general description. They are normally lower frequency because they require a lot of penetration. Okay, the curve is a wide angle, so you have a wide angle of view when you're looking at it. And again, we use it a lot for OB/GYN, babies. So we need a wider angle of view. Phased array probe. This is a unique probe. The phased array probe is normally a cardiac probe, and it's important that we realize that they're primarily used for cardiac. They can be used for the abdomen as well, but most of the time it's a cardiac probe, okay, primarily. But this is your image shape. It looks like a piece of pie. They call these probes sector probes or vector probes as well. So you may hear your sonographers say my sector probe's not working, and it's because they've learned it by a different naming convention, but they're the same probe: sector, vector, and phased array. Why is it the beam shape like that? Anybody have any ideas why we start off with a very narrow beam and then get wider as it goes deeper? Please. Through the ribs. Exactly why they do that. So, because we're trying to shoot a lot of times through ribs. And so as you do that, you want to start off with a very narrow beam form and get wider. Nice. So it's got a unique shape. It also has to penetrate a long ways, which means we're talking primarily lower frequency. 1 to 5 megahertz is pretty common on this one. Okay, 5 being pretty high frequency for a phased array probe. And between the image shape and low frequency, it's probably the worst image quality out of all probes. So you're really, you struggle when you're using like an ultrasound phantom to get a good image quality. Okay. Specialized probes, they're invasive. There's endocavity or endovaginal. They're wand-like, used for female pelvic exams or prostate exams. They're pretty specialized. There are 3D, 4D versions of that probe. Okay, so just know and be aware of what you have. One of the things we've run into a lot on these types of probes is damage to the lens, because a lot of hospitals and medical imaging centers have transferred to using a trophon or a trophon-like device, and it's caused a lot of damage, especially to the lens material and the cap. When it's a 3D, 4D probe, the cap will get loose and start leaking fluid, and you'll get some image quality issues with it. So you really need to pay attention on these to your lens material and your 3D, 4D if you're using a trophon, right? Specialized, again, TEE, transesophageal. Good news is you hardly ever have to play with these. It's a cardiac probe only, really used only on cardiac systems. They're fairly sensitive probes, meaning if you mishandle them, you can break them. You can damage them through mishandling very easy. So if you don't know how to handle one, you don't know how to unlock the moving mechanism, because there's a lock and a free, and people will be moving the tip of the probe when it's locked, and they're actually stretching and breaking the cables. And they don't know what they're doing because they've never been trained. So if you haven't been trained, try to find somebody in your facility that does have some experience. Call us, we'll be happy to tech support and talk you through it, show you some of the things about them. But these are very expensive probes. A common repair for these probes is a $12,000 to $18,000 repair for damaged probes. So very expensive probes. If you don't know how to play with them, take some time to figure it out, or have somebody educate you on them. We'll be happy to have a call with you and help you through that if you need it. They can also be 3D, 4D probes. Non-imaging probes, you have what they call a PEDOF probe or an OxyW probe. It's a very small, looks about the shape of a pencil. The scan portion of it's just a little bit bigger than a dime, about the size of a dime, if you will. And all it does is show you blood flow. It does direction and velocity of blood flow. There is no image associated with it. They're fairly inexpensive probes when you're talking probably around $1,000 range compared to 3 or 5, 6, 8 and up. So fairly inexpensive probes. 3D, 4D probes, again, there's different types. There's mechanical ones, and there's what they call matrix array ones that don't have any moving parts in them. Their image quality is amazing, but they're also very expensive. So again, the sooner you can detect a problem with a 3D, 4D probe and get it in for evaluation, the better it is for you, because for example, on a mechanical one, if all the fluid leaks out of it, you're going to get an image quality problem because there's air where there should be fluid. Also, there's a motor inside there that moves the probe head back and forth. Without the oil, without the fluid in there, it's going to be no lubrication, and it's going to cause damage to the motor, and then it's going to quit working. Now it's turned into a major repair. So a lot of things you can do if you just notice the problems early. Handling and storage. Again, one of the big ones is your TEE. If you don't know how to handle them, they should be stored in a HIPAA cabinet where they're sanitized and then put away, and then they have to be re-sanitized after 72 hours. They're very carefully stored. But any other probes, if they're in use, keep the cables off the ground. Use the cable holders if they're provided. You know, handling them and storing them will really help you. An example that I like to point out is a brand new Philips Epic. If you guys have had them or seen them in your hospital, the probe cable goes from the bottom of the probe down to the ground and lays right on the ground in front of the caster, and then comes up where they hang the probe. And that sounds bad already, right? But what you don't realize is if you move the machine when it's in this configuration, you roll over that cable, it yanks a connector out of the front of the system. And that board that the probe's plugged into is actually two boards. It's a module, an acquisition module, and that part is like $10,000, $12,000. So you just damaged the probe because you yanked it out of the connector. You damaged the probe, the board it plugs into, which isn't one board, it's a module, and that module is 18. So you're talking 15,000-ish to get the board repaired and replaced and a new probe. Keep your cables off the ground. I mean, that's the message. I walk through hospitals, you know, when I'm helping out, and I look into a room and I go in and I pick up the cables. It just bothers me. But things you can do to protect your cables, your system, your probes. Cleaning and disinfection. I don't spend a lot of time because every manufacturer has their own, you know, recommendations. Don't use alcohol. You can use an alcohol, but it can't be over 7%. Everyone's a little different. We can help you with that as well if you need a, you know, what do those GE recommend? Well, we can help you with that. But I have some information here. Don't use harsh chemicals, especially on the lens material, because it'll soften it and cause it to just kind of wash off over time. So be careful with what cleaning solutions you're using, and definitely follow manufacturer guidelines. And even that, I hate to pick on it too much, but GE, let's say 15 years ago, in their manual said, do not use harsh chemicals and heat to clean your probe. And then they partnered with Trophon, which uses harsh chemicals and heat to clean your probe. And then they changed all them, so it doesn't say that anymore. But the fact of the matter is, harsh chemicals and heat will cause damage to your probe over time. So I'm not picking on GE or Trophon because there's other manufacturers out there too. It's a really convenient, really cost-effective way as opposed to Cydex, which was hard to maintain, but it does have a negative effect. So just keep that in mind. Watch it, okay? Anyway, there's different types of probes and how they're used as far as what type of sanitation or decontamination you need. If you're using a TEE probe, they have very specific guidelines that you have to go through. They have to go through sterile processing. So you have a lot of things that you need to be aware of. If it's just a body floating BF probe, which is just anything surface, just wipe the gel off at the end of the use and then use a soap and water is fine. You don't have to get super fancy with those. It's when you get into the endocavity or TEE probes, the process becomes a lot more critical. Okay. Physical inspection should be performed regularly. If I go in to work on an ultrasound and it's just a general call, I can't send a study to PACS. I go in there, I look at my probes right there, and I look at them. Why? Because early detection benefits us. It means that I can stop it before it's a major problem. So whenever you're in front of an ultrasound system, take the 2 minutes, 5 minutes, it depends how many probes they have, but at least the ones on the system, if they have them in a cabinet put away, I maybe won't see those, but the ones on the system, you can take a quick look at and see some damage and correct it right away. So anytime I'm in front of a system, I take a look at the probes. They are high failure items. They're used every day with the ultrasound. So take a look at them. TEE probes, again, the completely different process to clean them. They have a whole department, sterile processing in hospitals used. They're set up to do this. It's great. Just make sure your hospital's got the guidelines and is following them because that can cause real big problems with patient safety. Okay. Common failures, and this is where we want to talk about how you can look at them, right? We've said to inspect them. Acoustic lens and membrane damage. You can have holes in the lens, especially if they're doing biopsies. They'll do the needle guides and stuff, and you'll see that they'll get damage to the lens. If they clean them with a harsh chemical or even a rough cloth, sometimes I swear they're using sandpaper to clean them because the corners are all worn off and exposed right to the crystal. So, which causes a lot of problems to image quality, electrical safety. Cable and strain relief damage. This is fairly common, believe it or not. To have the cable separated like that. And to me, it looks bad. One, I don't want to be the patient looking at that as they're scanning me with it. I also don't want to see the hospital white tape wrapped around it. It's dirty because they tried to hide that. It needs to be repaired, and the repair is fairly inexpensive. You're not replacing the whole probe. You're getting a new cable jacket. Sometimes they can take that cable jacket and get it back in there and put adhesive on it, and it doesn't even require a new jacket. So again, keep that in mind. Connectors. Connectors can get damaged. And some connectors, especially if the probes have pins on them, can cause problems to the system. And I don't know if any of you are familiar with the IE22, IE33 systems. They have a bunch, hundreds of probes on there, and they get bent pins on them. And I say it's contagious. And nobody goes, what do you mean it's contagious? Yeah, because they'll get a dropout on their monitor. And they'll say, is it a probe problem or is it a system problem? I don't know. So they unplug the probe and put it in a new port and jam it in that connector. Dropout's still there, so it must be a probe problem. Well, now they have two damaged connectors on their system. So they get a different probe, and they want to make sure it's not the probe, so they get a different probe and they plug it into the damaged connector, which bends the pins on the probe. And they still have a problem with it. Stop. Look at your probe, look at the connectors, and if either one of them are damaged, don't plug them into that port. Get either the probe or the port fixed, because it'll just, the worst one is I had to replace that board, and it's a horrible job. If you haven't scanned head select board on a 22, it takes you probably 2-3 hours if you know what you're doing. And then I had to replace 4 probes because they just kept plugging it into a bad board until they finally, I'm out of probes and I can't use the machine. I'm like, well, could have done that on the first probe. So crystal element failure, fairly common, right? You drop a probe and now you have crystal failure. It doesn't have to be crystal failure. It can look like the line on the left there, right here is a dropout. Everybody said, well, that's a crystal problem. That could be a cable problem too. It could be a problem with the ultrasound machine on your transmit or receive board. You have to figure it out On this case, I'd do multiple probes in multiple ports, making sure my pins aren't bent, right, if I'm going to move them around. But you want to try to figure out if that's a probe problem or a system problem first. And the easiest way to do that is put the probe in a different port. If it moves with a probe, try a different probe in the same port. If it goes away, then you know it's a probe problem. If it doesn't, and it's on multiple probes, then you have a system problem, and you can start working it. But clearly, probes are a high failure item, so we want to deal with that. I just want to make sure we're not. There we go. So let's move on here. Cracked. You can see the connector or the casing on top, excuse me, is got the crack in the corner. Fairly common. That's what happens when they drop, they hit the floor, they crack the casing. And that causes quite a few problems. One is fluid intrusion. If you're using it with gel, it can get fluid intrusion, causing damage over time. So again, the sooner you see that and get it repaired, the better it is. It's probably just going to take a new case and be done with it. It's not a big deal. It also causes an electrical safety problem potentially. If you can get fluid intrusion in there, it's going to go to the electronics, and then you're going to be able to shock the patient. And anybody had anybody shocked before with an ultrasound probe? Anybody even heard of it? What did they describe it as? Do you know what it? Yeah, pinprick, or you pull the hair. It feels like a pinprick, and pull the hair. Okay, it's not very comfortable, and it seems to happen on the same probe all the time. Well, this is an indication of what happens. The other bad thing is that can pull a hair because it's a crack. So if a hair gets caught in there and you're moving the probe around, there it goes. So now you don't know if you have electrical leakage or you pull the hair. Yeah, it's bad. So get them repaired. Again, the cost of the repair right now, if you notice it right away. But if you just wait, and a lot of sonographers say, I don't have an image quality problem, I'm just going to keep it in service. Or I have a dropout, but it's on the very right-hand side of the image. I never look at the right-hand side, I look in the middle. So I'm going to ignore it. Well, ignoring is a bad thing, okay? So stuff like this we can fix. It's fairly easy. There's a lot of third-party people, OEMs, that can take care of problems like this for you. Find a trusted partner and get it taken care of when it's affordable. Fluid invasion, a major problem with TEE probes especially, but even the one above with a crack in it, once it gets fluid in there and it starts wearing away on the electrical components, it causes corrosion. It's a big problem. Major cause of catastrophic electronic failure. It's just a problem. Earlier you can detect it and get it fixed, the better it is. The longer you wait, the more expensive it's going to be. Physical inspection. Again, I do them all the time. Anytime I'm in front of an ultrasound system. Immediate repair. If there's visible damage or if the probe is malfunctioning during use, it should be repaired immediately to ensure patient safety and accurate diagnostics. Okay, and it should say diagnosis, but bottom line is if you have any image quality issues, if you have anything that makes you feel like this is not, it's substandard, a crack, a missing lens material, electrical safety is not passing, it's leaking, anything like that, get it taken out of service. Try to get a loaner so you're not without the probe, and get it evaluated. I know our company offers free evaluation. So we'll send you a loaner, you send it in, and we'll say, oh yeah, it's just the lens material. It's going to be X number of dollars. And you can make a decision at that point whether you want to go with a repair or replace it. Regular maintenance checks. Again, I recommend 2 PMs a year on ultrasound. And GE learned it for everybody. They just put in their service manual that no PMs are required. But you need to read the whole paragraph because it says no PMs are, because there's no moving parts that um, excessive wear, cause excessive wear, PMs required. However, it keeps on going and says that there are other things that need to be checked. And you should do, for example, your filters weekly. Well, if you don't do any PMs, I can guarantee the sonographer is not going to check their filters weekly. So if you're not doing a PM every 6 months and they're not doing the weekly checks, the filter never gets checked. And when you get in there finally, because the machine's turning itself off because it's overheating, you'll find a blanket. It's a beautiful wool blanket, but it's not a mystery as to why the thing's failing. I highly recommend 2 PMs a year. It takes 2 hours. If you take your time and you know what you're doing, you can go through a PM, a thorough PM in 2 hours on most ultrasound systems. If they're portables, it's much faster than that. Highly recommend them, which allows you to inspect your image quality and your probes, make sure they're electrically safe. Again, if you ever have any issues, you can call us up. We have 24/7 tech support. We'll be happy. Unfortunately, I'm the 24/7. Okay, so I have my business cards here. I'll walk around and hand them out before we get out of here. But please, that's what we're experts on ultrasound. I don't do anything else. But if you need any help with ultrasound, I'd be happy to help you out. So what makes your probe unrepairable? Severe physical damage, and it is severe at this point. I mean, if it's a cracked case, we can fix it. Okay, but if it's a cracked case that you've let sit there for 3 years, and now you've had fluid intrusion sitting in there, and it's all the cable is corroded, all the connections are corroded, all the electronics are basically failing. We can't fix everything in a probe. It's not repairable. Then we just tell you to buy a new probe. So again, routinely check your probes if you're in front of an ultrasound. Should be at least every 6 months if you do PMs that way, right? Even once a year is better than just doing GE, no PMs required, right? Internal component failure, it happens. What's a common failure that everybody sees on probes when an internal component fails? That's one that we get calls on all the time. Sorry? Noise is one, yeah. How about no, my probe won't ID? Okay, they drop the connector onto the ground. They just drop it, and for whatever reason they plug it in. Now it won't ID. And it's fairly common failure on a probe, and they plug it into different ports and it won't ID. They do a different probe and it works fine. Well, it's probably internal component got damaged and it won't ID. So it happens. So just try to take care of it. Water or liquid damage. I know none of us would ever think about dropping the whole probe in a bath of water, but it happens. I've actually had a nurse do it, and they told her she needed to clean this probe, and so she did. She took it and she put it in a sink of water, cleaned it, and took it out and dried it, and then the probe didn't work. Be careful what we ask her for, but nobody told her she couldn't put it in a sink of water. It wasn't like doing dishes, I guess. I don't know. Inability to meet imaging standards. I can't tell you how many probes I see in the field. I go in there and I turn on the machine, the probe comes up and it's got a dropout. I don't even have to do anything. It's got a big dropout, and they continue to use it. Not only is it a problem for just image 2D image quality, but it's also a problem when you're talking Doppler noise. if you looked at, and I teach a class, it's a full day ultrasound basics class, and in it I show you the Doppler signal between one that has 2 bad crystals in it versus no bad crystals, and you can't believe the difference in a Doppler signal when you have only 2 bad elements in it out of 128 or 192. So it can make a huge difference. So sonographers need to take those out of service, and that's your job when you evaluate them, right? Get them a loaner. You know, if they can't live without it, some can't. Get them a loaner, get it out of service, get it repaired, get it evaluated. If it's a cable, they can replace the cable. If it's the array, it's a new probe. But at least it'll be you know, your diagnosis will be accurate, okay? And that's what we're really looking for. Inability, we already did that. Cost of repair versus replacement. This isn't really something, but at some point, you know, you have to make a decision. Is it more effective for me to repair it or replace it? And to me, that's where I just talked about it. If it's the array damage, a new array is the cost of a probe. I mean, you might as well just get a brand new probe or at least a refurbished probe, because it's gonna be not cost effective for you to repair just the array on a probe. Pretty much anything else, unless they're potted probes. Potted means they put like a epoxy over the electronics, and you can't get to the electronics to repair them, even if you know it's a bad cap. You can't get to the cap because it's covered in epoxy. So they call that potted, and a lot of the manufacturers do what they call potted probes. And you take the casing off and you go, oh, this is not repairable. If they just didn't do that, we could repair it. But a decision has to be made. The things I look at is if you have to get capital approval for a capital purchase to replace a probe, sometimes even though the price is the same, it's just better to repair it. We also, one of the things our company does is we'll send you a loaner probe. You send yours in for evaluation, and we send you a report back and say, you know, it's going to be $3,200 to repair it. It's got these 5 things wrong with it. And the probe itself is probably only worth $2,400. We can sell the loaner, we can just let the loaner for cheaper than it is to repair the probe, and we'll let you know that up front. And then you just keep the one that you've already been using, and nothing else needs to happen. So there's a lot of options out there for you if you're looking at repair versus replacement.